This is part 6 in a series of videos in which I'm attempting to repair a couple of HP9100B calculators. In the previous video in this series, I completely stripped one of the units down into its major sub-assemblies, took all the boards out, took the CRT out, stripped down the chassis, and what we're left with now is obviously a pile of boards and these assemblies. Now, while I don't normally go into a lot of detail with the sub-assemblies and the detailed static testing that I do, I thought I would with this particular machine, simply because certain aspects of it are so interesting and almost unique in the electronics industry. There are some features that were designed into this, and this was designed back in the 1960s, so very old technology but extremely advanced for the time. And it does make this machine a particularly interesting and historically important stepping stone in the development of electronics. Now, if you want to see more of this sort of explanation in future videos, then please leave a comment. But if you're not interested in detailed explanation of the way the actual boards work, then you might want to skip this video. But what I'm going to be looking at in this particular video is the main ROM board that's in this machine. So modern machines, you just have an EEPROM. They weren't really available in the form we have today back in the 1960s, and HP came up with a very innovative system that they built into this. And if you take a look at this or a cursory glance at this machine, then it can be a bit daunting because it has so many discrete components. It is a computer system in effect, but it doesn't have a central processor. It's all discrete, absolutely discrete, resistors, transistors, diodes, that sort of thing. And as I say, it can be a bit daunting if you're not used to dealing with this sort of equipment. But as long as you look at it in terms of a logical machine, then you can break it down into sort of various discrete parts and blocks, and it's a bit like you've decapped all the ICs in a more modern machine and you can see the inner workings of them. As long as you can figure out where each of the major nodes are in the circuit, you can just fault find on it in exactly the same way. Just don't be blinded by the sheer number of components. Just treat it the same way you would any other machine. So onto the main topic for this video is the main system ROM. And as I say, it's a very interesting circuit. It's actually underneath this assembly. This is the motherboard assembly, of course. If I flip this over, what we have on the bottom is the main system ROM assembly. Got a bit of corrosion on here, but it doesn't look too bad at all. So what I'm going to do is take this off the chassis. So it's just a matter of removing these two side PCBs. These are just kind of linked PCBs. They do have electronics on them, but I'm going to take these off and remove the main ROM assembly so we can have a closer look at it. Okay, I've removed the ROM board. We'll have a look at that in a minute. But the two side cheeks don't look too bad. Some of the contacts are opened up a bit too far, so they'll need to be checked. The tantalum capacitors, I may just replace those. These are reading okay, but it's only a matter of time before they tend to go short. And the rest of it doesn't look too bad. Now, there are signs on the edge connectors on here that they have not been making very good contact, so I'll give all those a good clean. You've got to be careful, you don't want to take the gold off, but there is some dirt on these that may well have been causing some issues, and especially on some of these edge connectors on the edge of the motherboard. And the other side cheek is pretty much the same. It just again needs a bit of a clean the contacts, but doesn't look too bad, so I can't see any obvious signs there's anything wrong with this. Now, when I was testing this, I was running it through the self-test, the diagnostic test, and it kept coming up now and again with failures, kind of random failures, and that may be down to dirty connections on this. It is very much a current driven machine, and it does require some fairly accurate control of current throughout the entire machine, and so dirty contacts really do cause a lot of problems for a machine like this. Have a quick look underneath the or the bottom of the motherboard when we've got this apart. So there's this shield, and then underneath this just looks like a standard motherboard. Okay, so nothing much to see under there. I will be going over this with a microscope and checking all the connections. Doesn't look too bad at all. I can't see any obvious signs. As with all HP machines of this era, it's very rich in gold, and so tends to last very well. As long as it doesn't start getting moisture between the PCB layers, then it tends to be in fairly good condition. The shield itself is very clean. The only thing that concerned me a bit with this machine is that a lot of the screws were either loose, a couple off the side cheeks were missing, so I think somebody's been in here before, and also a lot of the screws didn't have the correct washers on. Some of them were missing completely, so I don't think we're the first in here, but let's see what we can find with the main ROM board. So I'll just get that onto the bench. Okay, well here we have the main ROM assembly. Absolutely fascinating piece of electronics, and the key to this is this center board. Now this is actually a 16-layer board, and I'll explain in a few minutes exactly how this works, but all the information that is in the ROM is really stored in the physical arrangement of the tracks on each of these layers. Now, as I said, this machine was showing some intermittent behavior, and there is a bit of corrosion on some of the connections on here, so that may well be what's causing it. Again, this looks like an absolute nightmare to work on, but it's actually very straightforward. It's just the same circuit duplicated many times. So what we have over here is a decoder, and this is really nothing more than steering circuits, and we have a big bank of diodes at this end. And really what we are looking at here is a series of switches, steering diodes that allow currents to be passed through various tracks on this center board, and then the two boards, top and bottom, as you're looking at it, are amplifiers. They're sense amplifiers to pick up small signals that are output from this center board. If you've seen my series on the core memory, then it's a kind of similar sort of idea. This is not core memory, this is inductive memory, and I'll explain how it works in a few minutes. But in essence, this is just an amplifier or series of amplifiers to pick up small signals from the output of this, and it turns it into a logic signal. Now it's not logic 5 volts, this is a 15 volt or minus 15 volt system, but it works in a similar way. It's just transistor amplifiers, and if you're familiar with the way that bipolar transistors work, then you can look at the schematic and it's very clear. Each of the individual amplifiers is actually quite straightforward. There are a few complications with this, but as I say, I'll go into the way this works in a few minutes. But in terms of testing this, it's actually not that difficult. The core itself you can test fairly easily. If you look at the schematic, you realize that each of the inputs and outputs to this board are actually single tracks, and they go all the way through the board. So you can just get a multimeter, you can set it to ohms or continuity, and what you can then do is just start checking each of the expected paths for conduction. So for example, we should have conduction here, which we do. We can check the next one. You can go through. If any don't make contact that should, then obviously pretty much game over with this board. There's nothing you can do to repair it unless it's just a faulty or dodgy connection. But in essence, you can go through and check every single expected path. There aren't that many, so it's not like it's going to take hours and hours or days to do. So I'll go through and do all the rest. Assuming I don't find anything with this, you can do similar testing on the amplifiers. They tend to be fairly robust. It's generally only if you've had an issue with them that you're going to get any real problems. I haven't really seen any major issues with this. We do have a discolored resistor down here, So I need to check what this is. It might just be one of the tantalum capacitors is starting to fail. And the rest of it, there's nothing much else you need to look at. The diode bank, again, you can test that while you have the board out statically. On the other side, there's not that much to see, but I think I showed a current sense probe that I have, and this side of the board is exposed when this is in the machine. And you can use a probe like that to look at each of the individual paths going into the core and make sure it's being driven, and then see if you're getting the expected outputs. So it's nowhere near as difficult to work on as it first appears. It's just really a case of thinking about it logically, looking at each of the individual sub-circuits, the amplifier circuits, and see if they are doing what they're supposed to. Doing static testing first will allow you to eliminate a lot of the possible problems, but once you get the machine up and running, you can flip the entire assembly upside down with it out of the machine and start probing around on the underside of this board. Unfortunately, it's quite difficult to work on if it's hooked into the main motherboard, because you can't get to the top of it very easily, and it doesn't really work very well if you try putting long jumpers on these to allow you to run this outside of the machine, because, as I say, it relies on inductive fairly short duration current pulses, and tends not to work when you have long leads in the way. Having said that, if you can figure out which particular bit or line is not working, you can normally trace it through and fairly easily find the culprit. The most likely causes on here are, assuming the center core's okay, are the tantalum capacitors or the driver, the output transistors for the sense amplifiers. The rest of it tends to be fairly robust, so fingers crossed we're not going to have too many problems. Now, I just want to explain how this works, because if you haven't come across this technology before, this really is fascinating, and understanding how this works really helps in fault finding. So I'm just going to go over the basics of how this type of system works. As I said, if you're not interested in the detailed explanations, you might want to skip this part of the video. I've got my Dave CAD Junior CAD program here, so I'm just going to briefly explain how this type of memory system works. It's fairly straightforward, and once you understand the basics, it's quite easy to fault find with. Now, really, it's an inductively coupled, it's basically thousands of small transformers formed by PCB tracks. So the way that this works is you have a pair of conductors, and they're looped around and connected at one end, so they form a closed loop, and at one end there is effectively a differential amplifier. It's not arranged like that in terms of the circuitry, but this is what it really amounts to, and then you get an output from the amplifier. And to get the signals coupled from the incoming drive signals to the output, there are a series of traces that are arranged in small loops, so they'll be arranged like that. So if you pass a current through this wire, then it will cause a current to be induced in this loop. So this really forms a single turn transformer, and that causes a current to be induced in this loop, and that in turn will give you an output from the differential amplifier. But as with any ROM, what you really want is a better return for your money, so you want more than one bit per drive signal. So this is your drive and this is your sense. So what you do is you arrange more than one of these loops. So it would be arranged like that. And so this would be maybe bit 0, and then this could be bit 1. They're arranged in an array, so if we have the same arrangement for the loop passing over these sense lines, then we'll get a current induced in the same direction and we'll get the same output signal. So let's assume that this gives us a 1 as an output. If on another drive line we have a signal like that, then again we will get a 1 out of this sense amplifier when we pass a current through the drive. We'll call that drive 0, we'll call that drive 1. But if what we do is this, then when the current passes through this loop, it's obviously going in the opposite direction. So in this one it would effectively be going that way, and in this one it's going the other way. So in this case the current would be induced in the opposite direction in the sense loop, and that would then give us a negative output from the sense amplifier. So in this case, if we energize D0, we will get 1, 1, and if we energize D1, we will get 1, 0. And if for the third loop, for example, we arranged it like this. I'm showing these slightly offset just so you can see, but they are directly overlaid in the actual PCBs. If we call that D2, that's drive 2, then when we pass a current through this one, what we will get is 0, 0. And it's as simple as that. That's all that's done. It's arranged slightly differently from this, just to keep all the lengths of the paths the same. But this is how it's arranged in terms of the coincidence between the sense lines and the drive lines. It's slightly cleverer than this. If we look side on, then this is obviously two sides of a two-layer board. So we'll have, for example, the drive lines on the top and then the sense lines on the bottom. But what you can then do, of course, is put another layer underneath to give you another layer of drive lines, and you can then reuse the same sense lines. And then underneath that you can put another sense, another drive, so you can stack all this up to give you very good density. And I think they got something like 1,000 bits per square inch, which doesn't sound much by today's standards, but at the time was astounding, considering it wasn't using any active components for the actual storage. It was only using the physical arrangement of the tracks on the board. So that's the basics of how it works. If we look at this under a microscope, you can see that the copper trace is here. I've put some marks on here to indicate the current loops. These form the individual bits, and you can see this arrangement looks a bit odd, but it's to keep all the current paths the same length, and you can see how some of these swap over and form current loops in the opposite direction. So this is how it's arranged on the individual layers. The copper traces are the drive lines, the black are the sense lines, and you can see that as each of these loops passes over the sense line, it forms a coupled loop and will induce a signal in the sense line if a current is passed through it. Okay, so to further try to clarify how this works, what I've done is build our own version of it. So this is just 4 bits, but I'll get this powered up and we'll demonstrate it working. It's quite hard to demonstrate because as with the core memory, the output signals are very small, but I'll try and demonstrate this, and hopefully it will further clarify how this works. Okay, I've got us all hooked up, and all we have here are 2 drive lines. So we have the orange is a drive line, the blue is a second drive line, so we'll call this drive 0 and drive 1. The brown loop is our sense output 0, the white loop is the sense output 1. And the 2 switches on the right just allow me to put a pulse of current through the drive line, and whichever one I push, of course, it does put a small current. It's only about 50 milliamps, but it's sufficient to give us an output. and then the two channels of the scope are connected to the two sense outputs. Now the signal outputs are relatively small, and in the actual ROM board itself, these are connected to small transformers that step up the voltage and basically condition it, and then there's a sense amplifier that turns the small signal output from the sense lines into signal outputs that are used to drive the machine. But what I'm going to do here is just demonstrate the way that this is actually meant to function. So in the first bit, we've got 4 bits here. The first bit, you can see that the loop comes down, so it's going down. Effectively it's an anti-clockwise loop, and then in the next one it swaps over, and the second bit in the same drive line is a clockwise loop. In the second drive line, we have the first bit is an anti-clockwise, so it's still the same as the first one, and then the second one is also anti-clockwise. So what we have here is, depending on how you want to look at it, a 1 and a 0 and a 1 and a 1. So if we energize the first drive line, we'll get 1 0 out of our 2 sense amplifiers, and if we energize the second drive line, we'll get 1 1 out of the same sense line. So we'll try that. So I've got this powered up. We'll do a single capture, and I'll press the button on the first drive line, and you can see that what we have now is a positive going signal on the first output and a negative going signal on the second. Ignore the ringing, that's just because of the way this is arranged. It's very difficult to show this on something like a breadboard because of all the wires that are trailing around. So we'll just repeat that. Another single capture. Notice it's very repeatable, but we are getting a high and a low. So in other words, they are inverse. If we now do the same thing, but I press the other button to energize the second drive, we are now getting a high and another high. Again, there's some ringing on here, but hopefully you can see that these signals are both the same polarity. And we'll just repeat that. You can see that it's very repeatable, and this is what we expect because both of the loops in the drive line are anti-clockwise loops, so we should get the same sense out of the sense lines. And if we do another drive for drive 0, again we are getting a negative output from the second sense amplifier because the loop is going the other way. And that's exactly how this works. The way it's arranged on the main ROM board is, I think there are 32 of these loops in each drive line, so we get 32 bits out for each drive line, and all that we have to do then to get the data out of the ROM board is to energize the appropriate drive line, and then the sense amplifier outputs will give us the data that we're looking for. And it's as simple as that. It's just a decoder, energize the correct drive line, and then look at the data that comes out of the sense lines. And the data that comes out of the sense lines will be entirely dependent on how the tracks are arranged on the board and which direction the coincidence loops are arranged on the adjacent layer. Hopefully that made sense. If not, then let me know and I'll go over this in a bit more detail, but hopefully you can see this is quite straightforward. It's not particularly complicated. It just looks very complicated because of the sheer number of components on the ROM board. But it's an absolutely amazing piece of technology for the 1960s, and I think it makes this particular machine one of the most interesting that I work on. And it's these 9100s are probably well worth investigating. Even if you only look at the schematics and the documentation, they are incredibly interesting. Hopefully you didn't find this too boring. Some of the other circuits in this machine are, in my opinion, equally interesting, so I will be doing some mock-ups of some of those as well. And if you're obviously not interested, then skip the videos, but conversely, if this is the sort of thing you want to see more of in the future, then please let me know.